Hi, folks. Welcome to the latest in the talk series on advanced topics in programming languages. As I start every single one of these talk series, talks in the talk series with, I would like to just make a quick plea for people who are interested in various topics in programming languages to come and give talks. I see a lot of people who have given talks, but I see a lot of people whom I know a lot about a lot of topics and have not yet given talks. So please come up to me and tell me, I would love to give a talk, and we can set something up. Today we have a talk on a topic which should be near and dear to the heart of every Googler who writes C++ programming, because this is coming down the pike really quickly, and everybody needs to know about it. It's from Lawrence, who's given several talks on C++ standards. He's very involved in the C++ standards process. And today he's going to talk to us about multi-threading in C++ and the changes that the standard has in store for us with respect to it. Lawrence.
Can you hear me? Good. I'm going to start off with the introduction, but my real reason for starting with this slide is to let you know that when one of these types of slides appears, that means I'm about to make a significant topic shift. So if you've been sort of sitting on a question, one of those topic shifts would be the time to ask it, because I'm going to move on to something completely different. The first thing I want to talk about is where this all fits in. There's quite a number of changes to C++ coming with the next standard, and one of the major goals is to extend C++ into concurrency. Right now it's a serial language, and that's no longer acceptable. But an important feature of C++, and one of the major reasons for its success, is it lives within a computational environment. You can include the system headers, all this kind of thing. So C++ is connected to the rest of the world. It's not an isolated language. And we want to preserve that feature as we move forward into concurrency. And finally, C++ gets a fair bit of its power from being able to let good library writers write good libraries. And we are going to be unable to provide the right parallel solution. So what we want to do is make sure that what we provide enables library writers to do the right thing for their application or for their industry and move forward from there. So what I'm going to show you today is, for the most part, a start, not an end. And for this talk, what I'm trying to do is just basically outline the primary features. I can't go into all the details, but I can give you an overview of where things are heading. And not all of this is stable yet. There's active debate within the committee about what to do. Some of the syntax hasn't been chosen. Some of the semantics hasn't been chosen. And because of all that debate, I would like to get from you feedback on where you think we're doing things right, where you think we're doing things wrong, and so forth. Finally, as this is dealing with the C++ standard, I have a set of disclaimers here, which means basically that you should take what I say today as a hint, not as an answer. So everybody has heard the story about multi-core processing and how it's coming, and we're not going to get single cores that are going to go any faster, so all the chips are being multi-core, and we're going to have to start dealing with multi-threading. And that's part of the story of why we need to add threads. The other part of the story is that it's now a connected world. We have each computer talks to the internet, and some of the ways you write programming is better in a concurrent world, even if you're still on one core. And so we're looking at those kinds of issues. The other issue, which applies less to Google's specific applications, but does apply to in other application domains, is some programs require very large machine resources, hundreds or thousands of processors. And those you can't do without some form of concurrency. So people are getting by today, and what do they get out of a C++ standard on all this stuff? Why isn't POSIX good enough? Well, for one thing is it's not just POSIX. It's also Windows. It's also embedded systems. It's also mainframes. There's a wide variety of machines out there. And while the model is dominated by Windows and POSIX, it's not solely Windows and POSIX. So we'd like to create a portable expression of programs. The other thing that having this in the C++ standard does is it creates a bigger community to talk about parallel computing, concurrent programming, and so forth. So some of the solutions that people create, if they create it in a standard environment, it'll spread to a wider community, and a wider community can work on it. And that's a big leverage on the work that all of us are going to be doing. The next big approach we're taking is to standardize on the current computing environment. So we're not going to try and invent a totally new model of parallel processing in the C++ community. The world is littered with parallel computing languages that died. And so we are going to standardize on a model that is well supported by the current operating systems. And we have strong belief that those will be around for quite a while. So we have one C++ thread will be one OS thread. It's heavyweight, independently scheduled, preemptive, etc. So that cost model is exactly the same as what you're used to with POSIX or Windows threads. The second major bullet point is it's shared memory. The variables of the threads are all shared among all the other threads. There's no isolation of memory. And this, too, is in common with POSIX and Windows threads. The big point we also need to make is that we are not trying to compete with other standards. There are standards for message passing. We're not trying to displace that. There's OpenMP, which is a standard for sort of hierarchical, loop-based programming. We're not trying to replace that. We're not trying to replace automatic parallelization in compilers. So we're really trying to sort of provide a standard access to the environment. And we have a sort of a split view of what we're doing on this. And this view is a little fuzzy, but two sides. Changes necessary to the core language to make this all work, and changes necessary to the standard library that give you a library interface on some things. Now, this separation isn't entirely clean because sometimes they overlap. Some things that look like a library interface are in fact a core language change. So it's a bit fuzzy there. But overall, you can think of this split. And the core language, we're really concentrated on what is memory, what are variables, and when two threads touch a variable at the same time, what happens? What does that mean? That's the kind of core level changes. And this core language change area is where I'm going to be spending most of this talk for two reasons. One is I know more about it. And the second is that this area of the language is more baked right now. The second area is in the standard library. And this focuses on how threads are created and synchronized, and how we deal with what happens when a thread stops, how do we make a thread stop, and layers beyond that. Yes?
So when you, first I want to know if reading a string simultaneously from two threads is safe, does that fall under core language or library?
Well, the string is an abstraction put out by the library. So there's actually a slightly subtle answer here, but it's important. The answer is that if you are talking to the same variable, then you must do the synchronization. The standard library, by design, is not going to try and synchronize a variable. On the other hand, if, as is common with many implementations of string, they have reference-counted objects, then the standard library is ensuring that any object shared between two variables is properly synchronized. So you are responsible for the shallow synchronization on the variable, but any deep synchronization is the responsibility of the library.
Can you repeat questions again?
I'm sorry. The question was whether or not things like string are synchronized in the library or not. And so the answer is halfway in between. Yes?
Will there be any thread local storage?
The question was, will there be any thread local storage? And I ask you to wait a bit. So my first topic is, what is memory? The traditional notion of shared memory that everybody thinks about is that you write a value to memory and it's instantly visible to all of the other threads. This is sort of what we thought about in the past, what people tend to think about when they think about shared memory, but it doesn't work. Among other things, it implies faster than light communication, and we've pretty much ruled that out over the last century or so. It doesn't match the current hardware because they have speed of light limitations as well. And in addition, current modern compilers, even in the serial case, will apply optimizations that make that not true. So for all of those reasons, you're not going to get an instant shared memory. So there will be some lag between when you write a variable in one thread and when somebody else gets to see it. And we're sort of nominally terming this message shared memory. So you have two threads and they want to communicate. One thread doing its writes, those writes are sort of held up in limbo until you write to an atomic variable or acquire a lock. And then those get communicated until another thread accessing that same place picks those writes up. So two threads are mediated through special variables.
Is it release consistency or acquire consistency? Yes.
It's detailed. I'll get to that a little bit later. So the mechanism here is acquire and release. So a variable, when it writes to a thread, when it writes to a variable, says, I release all of my writes to this variable. And then somebody coming along later says, OK, I want to do an acquire from that variable. And all of the writes that the one thread did are now visible in the second thread. OK? And so we have a store release and a load acquire, which is sort of the base mechanism of how this stuff happens. So typically, you release things when you do a store, and you acquire things when you do a load. There's also, yes?
If you don't do a release, does that mean that if another thread tries to acquire variables, will be see the old version, or is it non-termination?
I'll get to that in a minute. Modern machines also have the notion of a memory fence. And the proposal right now for the C++ does not have memory fences in them. And the reason for this is partly the definitional process, partly that there are some proposals that are in their early stages. We don't know quite what's going to happen. But the major thing here is to take away is that the current machines have fences, but the current proposal does not. And we don't know how that's going to settle out. Partly we keep talking about them because in terms of implementation, when we say this C++ language construct implies these certain barriers on modern machines, these certain fences on modern machines, we're trying to get an estimate of the cost. The main problem is there might be, we might inhibit future architectures if we put fences into the language. So because we are communicating through shared memory, the sequencing becomes an issue. So within each thread, we have a sequence of operations, and then we write to shared memory. And now we want to ask questions about how do threads sequence, how are reads and writes between threads ordered. But in order to solve that problem, we have to first back up to what happens in the single thread case. And the old model for sequencing was these sequence points in the old C and C++ standards. And those are not well founded. Nobody really quite knows what they mean, various other problems there. So the committee has done a significant amount of work, and sequence points are now gone. And there are a couple of ordering relations. The first one is sequenced before, where there's a strong sequencing between operations. And then the next one is indeterminately sequenced, where there's sort of a weak. It has to be either entirely before or entirely after, but I can't tell you which. And the key idea here, the key point in the standard is that if you do a couple of writes or a read and a write to a variable, and those operations are not sequenced, you now have undefined behavior. Okay? So we don't try and make it defined, and it's up to you to do the right thing, you and your compiler vendor, if they give you warnings. So, but that's undefined behavior if you don't properly pay attention to your sequencing. So that's the sequential case. Now we get into the parallel case. And the main relationship we have here between operations is sequenced before. And that comes from the serial case by adding to the serial case the acquire and release operations on variables, which then get picked up in another thread. So if you have intra-thread ordering, you zip over to an atomic variable, pick that up in another thread, and now you have those operations are now sequenced before each other across that connection through memory. Okay? And put all of that together and you have a happens before relationship between two memory operations in different threads. And here's where the hard part comes in. So, data races. If you have a write to a regular variable, not atomic, but a regular variable, and some other thread either reads or writes to that same variable, without this happens before relationship between those two, then you have a race condition and your program has undefined behavior. Now, I want to be clear here. Undefined behavior means, yes, you just did order 1,000 hogs to be delivered to your front door on Tuesday. Okay? Really, the standard can't say anything about what's going on because you're suddenly getting random word tearing, wild pointers, all that kind of stuff. So the standard really can't say what's going on. So you get undefined behavior.
But you also would prevent useful non-deterministic programs from being implemented, right?
So the question is, won't you also be preventing useful non-deterministic programs from happening? The answer is, no, that's not true, but you can't use regular variables to make that happen. You have to use atomic variables to make non-deterministic programs happen. In that last slide, I sort of slid by this a memory location. And just waving our hands like that is not quite good enough for the standard. So we have an actual concrete definition. And that is a non-bit field primitive data object, or a sequence of adjacent bit fields with some weasel wording. So the idea behind all of this is to avoid having to do atomic read, modify, write operations to access bit fields. So we're going to continue with the current compiler notion of read the bit field and all the bits around it, change the part that has your bit field, and write it back out. And if there's any collision between two threads, that's a data race and you have a problem. So If your bit fields really do need to be atomic, then you have to go to extra work to separate them in memory. And for people that are working in binary worlds, this will also change the layout of your structures in memory, could increase the amount of memory you use, could change compatibility with existing libraries. So be careful in that location. Now, this model of memory and data races and so forth does have an effect on optimization. It's not entirely free. There are some speculative reads and writes that current optimizing compilers have been known to do that will no longer be legal. And the reason is that when you're compiling some function, you have no idea if it's in a multi-threaded application or not. You might not know that it's in a context where the code can't be moved around or the writes can't be dropped or so forth. We believe that those speculative reads and writes will not be a major impact on program performance. We think it's in the low single-digit range. But of course, we can't guarantee that for all programs. There is, however, one case where we had to have a special rule, and that is the compiler can assume that a loop will terminate. There are a substantial number of optimizations that involve pulling code out of loops in front of the loop or behind the loop. And if the loop never terminates, you can't really do that kind of stuff. So we made the rule that you can assume that the compiler can assume the loops terminate. For the most case, this is nearly always true. And in the cases where the loops don't terminate, they typically have shared memory operations or locks or I/O or some other thing that would solve the problem as well. This really only affects tight loops that the compiler can't determine terminate. Yes?
What is a loop?
What is a loop? That's cyclic control flow arc.
Considering that these things terminate with interesting implications.
Yes. So in this case, the compiler does not have to determine that it's going to terminate. And this allows a lot of the current optimizations to continue to go through.
So the definition of loop doesn't include the control flow by exceptions.
So the question was, the definition of loop doesn't include control flow by exceptions. And if you create a loop via control flow, that is not currently covered by the definition.
It's probably also worth reiterating that if you perform some of these optimizations, you're not going to be changing single-threaded connections, right?
So the question was that if you perform some of these optimizations, you're not going to be changing across loops. You're not going to be changing single-thread semantics, and that's correct. OK, so we talked about memory and some of the interactions there, and we said that we're going to communicate reads and writes through atomics and locks. And now we're going to talk about the atomics. So we have to say what is atomic. And what we have is a set of atomic operations on a single variable. So the operation on that one variable is atomic. And those operations will appear to execute sequentially on the view on that variable is sequential to all threads. So they will see the same order of events in the system for that one atomic variable. So if thread A writes 2 values to an atomic variable, thread B will see those 2 writes in exactly the same order. Now, it may not see both of them because there's a certain resolution problem, but it will appear as though there's an inherent sequential order. We do not use the volatile keyword to indicate this. Java does use the volatile keyword. C and C++ have a longer history than Java, and we've been using the volatile keyword for many years, and we chose not to change its meaning. It still has the old device register meaning that it's always had, and it does not indicate atomicity. But you can have a volatile atomic variable, which says that there might be some external agent that changes this variable in addition to some other thread. So atomic is a notion between threads, and volatile is a notion to the environment. We also have a set of requirements on atomic variables. The first big one is static initialization. If you're using these things to synchronize threads that may pop into existence, you don't really want to worry about the threads starting before you've had a chance to initialize the atomic variable. So one of our key criteria here was we want to make sure that atomic variables are statically initialized. We also want a reasonable implementation on current and future hardware. So we didn't want to create some type of atomic variable that was inherently expensive on current hardware. They're all going to be a bit more expensive than regular variables, but we don't want to have huge costs. We'd also like to enable relative novices to write working code. Now, I want to warn you here that relative novices is a very small group. The experts are the people that publish in Principles of Distributed Computing and find errors in other papers on that same journal. So that's where the experts are. And then around them are people that sort of can do a lot of it, but aren't really experts. And incidentally, I fall in that category. So most C++ programmers are not in the category where we expect them to be using atomics. Our final criteria, one of our criteria is to enable those people that write the Principles of Distributed Computing papers to write very efficient lock-free code. We want to give them all of the tools to make the hardware sing. Because while that kind of code doesn't have to be written very often, when it does have to be written, it's performance critical. And we also wanted to leverage those very bright people that know how to do this kind of stuff. So we want them to be able to write lock-free libraries and give the rest of the world higher level data structures that do the right thing, where the users of those data structures don't have to worry about the gory details. Yes?
Question. Is atomic a property of a variable, or is it a property of the way you access the variable?
The question was, is the atomic a property of the variable or the way you access the variable? It's a property of the variable. I'll get to that in a second. The operations on an atomic variable have a couple of attributes. One is acquire, which we talked about. I want to get other memory rights. Release, I want to give my memory rights. You might also do both an acquire and a release at the same time. And then finally, you want to do relaxed, which is there's no acquire and no release implied. And that's where you get the non-deterministic behavior. So you're not necessarily synchronizing any of the rest of the memory, but you still do get that sequential view of that one variable. And the other memory ordering we get in here is fully ordered, where we get extra ordering semantics beyond what arises from simply acquire and release. The problem in all of these atomic variables is that too little ordering on your variables will break programs. But too much ordering slows the machine down substantially. and you need to find the happy balance. As it turns out, most programmers, when they write this code, should be conservative and put in too much ordering, because then you're more likely to get correct code. And then, when you find you have a measured performance problem, you might want to go back in and relax things a bit and use weaker ordering constraints. But once you start down that road, you need to take the attitude that you're writing public code and get lots of code reviews and so forth to make sure that it's working. And part of the reason for this is that people tend to think of a world in a consistent fashion. And once you start getting into weaker memory models, you don't get that consistency. And in particular, if you look at this code example, 2 threads independently write to independent variables. And then 2 other threads read those variables. And do they get a consistent view? That is there a system-wide total store order on X and Y? Some hardware does provide this. Other hardware does not. And systems that don't provide it can be faster, but people have a harder time programming without it. So what have we done? What we've chosen to do is, for the fully ordered atomic operations, we have made them sequentially consistent, because this is where people seem to be most comfortable in terms of getting correct code. It's a little bit less efficient. Slightly weaker models don't seem to have a good formalism. We sort of wave our hands and can say it's sort of like this, but we don't really have a good formalism. And we're trying to make sure that the language has a good formalism, because a good formalism helps programmers and compiler writers resolve any of their differences. And then we have weaker models that you can get to through explicit programming. So I'm going to switch gears a little bit. Now that we understand the background for the atomics, I'm going to sort of build up what they look like in code. Yes?
So in the previous example, all the operations of X and Y were ordered by default?
Yes. So if you use the operations that are syntactically most convenient, they will be ordered. Now, if you start writing more verbose code, you can weaken that.
Does ordered apply only to a single variable, or does it apply to the entire?
It applies to all variables. So if you are using only the fully ordered operations, you will have a sequentially consistent view of all the atomic variables. But once you start getting away from the fully ordered operations, things will get weaker and they won't look sequentially consistent. OK, one of the problems that the C++ language has to deal with is a wide variety of hardware. And in fact, we have some older hardware and some embedded hardware that may not have all the full hardware support that some of us have become used to. So the standard is built around one primitive atomic data type that you really have to have hardware support for. And this is the atomic flag. And it has test and set and like semantics. Once you've got that, you can build up the rest of the environment. It will not necessarily be the fastest thing you ever saw, but it should be sufficient. And at this level of programming, it's really down in the basics, and you want to stay away from this as much as possible. Past that, we have a few basic atomic types: a Boolean, a set of integers, and a void pointer. And you can build these from that flag that I showed you earlier And the proposal before the standard shows how to do that. But we expect people to go a little bit further than that. But those basic operations have a set of C-level operations which look like function calls, as I showed you in some of the earlier examples and as you see here on the screen. You can use these same operations from both C and C++. In C, they'll look like type generic macros. In C++, they'll look like overloaded functions. But core thing is you can write the same syntax and the same things will happen. And those operations include the ordering constraints that we talked about earlier. But we also have a C++ level to the operations. And here, those atomic types look like classes. And we have a small number of member functions and a small number of operators. And those are the fully ordered operations we talked about earlier. So when you write, do an assignment, you'll get an atomic. When you do a compare and swap, that'll be strong. When you do a plus equals operation, that increment is atomic and it's strong. That is fully ordered. But there's a problem here. And that is, if you look at a C++ class, it comes with sort of this default assignment operator. And that default assignment operator is wrong for atomic operations, because the compiler is going to generate a plain load and a plain store, and it won't work. So the simple answer is, of course, write your own assignment operator and make that atomic. Well, the problem is that if you write your own assignment operator, under the current language rules, that is no longer a pod data type, and it's no longer guaranteed to be compatible with C. And remember, one of our goals is to be compatible with C. So we couldn't do that either. And we can't really stop that assignment operator in C, and particularly C90. However, we've made substantial progress in the current language with a bunch of new papers that allow us to address this problem head on. And we can, from the C++ committee side, now prohibit the assignment operator without violating compatibility with C. And I expect that if the C committee adopts this work, they may well just prohibit the assignment operator as well. So one of the things I just said right there is prohibit the assignment operator. And the question is, why do that instead of make the assignment atomic? And the answer is, one, we didn't want to interfere with the C view. And the second thing is that people would see that simple assignment operator and think that the reading and the writing together were atomic. And given current hardware, we can't make that happen. We can make the read atomic, we can make the write atomic, but we can't do both together atomically. And so we invalidate the assignment operation so that users have to explicitly see the read and then do the write separately. Question?
So if you're going to disallow the assignment operator, why have plus equals and equals and all the other things? Why not just say no operator overloading for atomic type?
Well, let me be clear on which assignment operator I'm talking about. When I talk about assignment, that assignment operator, I was talking about the assignment from atomic to atomic. We still support an assignment from an integer to an atomic.
Oh, okay.
Right? And so all of these previous operators that you saw here, they're all taking in values. So 3, so you can read from an atomic variable. You can write to an atomic variable with an integer. What you can't do is simultaneously read from an atomic variable and write to an atomic variable in an atomic assignment operation.
So you're prohibiting an atomic on the right-hand side of
I'm prohibiting an atomic where both the left hand and the right hand are atomic variables. So question.
So are you saying that line 4 there is stuff that doesn't work?
No,
That works.
that all works. Those are so basically what we're looking for is operations that have only one L value, right? If the operation has only one L value, then we can make it work. The traditional C++ assignment operator that's automatically created for you has two L values, one on the left and one on the right. And that's what we can't handle.
Wouldn't plus plus A, don't you have to read from A?
equals A plus 1, right?
Don't you have to read from A into plus plus A?
There happens to be
But it's the one variable, so.
It's one atomic variable, and we can take advantage of. So let me repeat the question. Doesn't plus plus A have that problem where you have to read from it and write to it? And the answer is it's one L value, and we can use fetch and add hardware to make that operation work. There is a change here that's a bit subtle. For the plus equals operation, as you would normally define it in C++, it would return a reference to its left-hand side. For these atomic operations, they do not return a reference because then you might read from it again and get bad results. So for these atomic operations, what they return is a value, which is surprisingly enough what C does. So we've kind of sort of come back a little bit. So you had a question.
Do you also lose equivalence between assignment operators, for instance, A equals A plus 4 versus A plus equals 4?
OK, the question is there an equivalence between A plus equals 4 and A equals A plus 4? The answer is no. The A equals A plus 4 is two separate atomic operations. There's a read, a regular add on values, and then a write. So there's very much a difference between those two. They're different operations. So question in the back. Can I do a race? I'm not sure I understand the question.
Array access.
Oh, so can I do arrays? There's no atomic operation over arrays, but you can do you can have an array of atomic variables. Question?
I guess I have to go back to my original question. With all of the differences between what is sort of intuitively expected by the C++ programmer and what this actually provides, did you ever discuss not supporting operator overloading for atomic variables?
So the question is, with the differences between sort of traditional C++ semantics here, did we ever discuss not having any operators? And the answer was yes, but nobody wanted really to do that. Particularly among the committee, whenever we wrote code, we almost never wrote out big function calls. We did plus equals. And so in a lot of cases, we just thought that it would be too much trouble. Okay. Your point is valid, though. So in addition to the C++ view of these basic types, we also have an atomic template which gives you a uniform way to name the types. So the other types were atomic underscore int. If you wanted an atomic underscore char, it was atomic underscore char. And those are two different names, and they're really hard to manage from within templates without writing a bunch of specializations and so forth. So what we have now is an atomic template. You can write atomic, left angle, int, right angle, and you get all those same semantics. And now you can put atomics inside of templates and make those things go forward. There are, however, some semantic restrictions on what you can put inside of this atomic template, what types you can put in there. The primary ones being it must be bitwise copyable, because we have to rely on those semantics with the underlying hardware. And they must be bitwise comparable. The compare and swap operation is a bitwise comparable operation. And that template has specializations into the basic types. And we also suggest how to implement this so that there are specializations onto the hardware for arbitrary types. So one of the things in C++ standard library is this notion of a pair. So if I have a pair of 2 ints, I'd like to be able to put that into an atomic template and have everything work. And with this formalization, it will work. So any small type like a nat, you can wrap with atomic, and things should work out pretty well. If, however, you wrap the entire circus with an atomic, we cannot implement that in hardware. So what we will be doing is putting in some locks around it and stopping the whole world while all of these things go on. And so while it works, we recommend you don't do that. So use atomic variables with care. The other thing about atomics is there's certain properties of freedom that keep getting labeled with these atomics. So I want to go through those because they do affect the interpretation of C++. The first and foremost principle is whether or not an atomic operation is lock-free. And this is important because if it has a lock and you crash it in the middle of the crash the program in the middle of the operation, or crash the thread in the middle of the operation, you now have somebody holding on to a lock, and you could get a chain of failures because that lock isn't released. Lock-free means that there is always somebody making progress, even in the presence of crashes. Okay? The next stronger capacity is wait-free. And what that means is that every operation will complete in a bounded amount of time. So you can get lock-free, but there may be arbitrarily long to make some of those operations finish. They will finish, but it may take arbitrary amounts of time. Wait-free means they won't take arbitrary amounts of time. And address-free means that the atomicity of the operation does not depend upon the address. Okay? This is particularly important when you have 2 processes sharing memory at 2 different addresses. So you have physical memory at 2 different virtual address spaces. And so this is where that property comes in. There are no support in hardware for lock-free atomics on big types. So those big types must necessarily be implemented with locks. And those locks cause problems when you get to signals. So you don't want your atomic variables to have locks in them if you're also using those variables with a signal, because they'll come in at arbitrary times. So we give a means to be able to test whether a certain atomic variable is implemented in a lock-free manner or not. So, well, we can't guarantee that the atomic variable you want to use to communicate with your signal is lock-free up front in the language. We can guarantee that we'll give you that ability to test it. And because certain processors implement lock-free stuff through dynamic libraries that are dependent upon the individual processor, we can't even know at compile time whether or not certain types are going to be lock-free. So it's a dynamic test for that. We also have preprocessor-based static tests that will tell you whether or not the basic types are always lock-free or never lock-free. And if they're not always lock-free and not never lock-free, you have to fall back to the dynamic tests. The second layer of freedom that I talked about was wait-free. And again, you need hardware support to make these things work. But that support is substantially less common. And when people write this kind of code, they end up writing fairly processor-specific code. And it's difficult to write portable programs in this realm. We also found that few of the people that were wanting to write with these atomic variables cared. Some did, but most didn't. So we're going to leave this property unspecified in the standard. We won't say whether or not it's weight-free. And the third freedom there was address-free atomics. Inherent in this is that there are two different addresses for the same variable. And that's outside of the C++ standard. C++ standard has no way to say that. But we recognize that people, in fact, do write C++ code that shares memory between processes and does so at different addresses. So we're going to try and help out here. What we're going to say is, if an operation is lock-free, it must also be address-free. That's the intent that we will put into the standard. We can't make it a firm requirement in the standard because we have no way within the standard to test that. But that's what we're going to say. We don't believe that that'll be a problem for any of the C++ compiler and system vendors. But that should then give people writing multi-process programs a leg up. And it should also help people that are mapping the same file into two different places in the virtual address space a leg up. Yes?
Have you folks thought about maybe incorporating things like transactional memory?
The question was, have we thought about incorporating transactional memory? The answer is yes, the committee has thought about that to the extent that we're pretty much agreed that while it's an interesting area of research, it's still an area of research not yet stable enough for us to put into a C++ language standard.
Actually, you've actually got another 35 minutes.
Yeah. Yeah, so I want to point that out. Some people are starting to get nervous that I'm not wrapping up. This is a 90-minute talk. So if it appears I'm not wrapping up, that's there for a reason.
You actually have a little bit more than I realized, which is for in terms of transactional memory, you actually do allow atomics over entire say struct, an entire class or an entire struct, and you could easily imagine that being replaced with the transactional mechanism should hardware transactional.
Right. But the atomicity we have over an entire struct is basically to load and store it. And you can do a compare and swap. They're very limited operations.
That's gestational.
Yes. So the next thing is that we have these variables, and in this multi-threaded world, what happens to the variables? We've got three major areas. The first is thread local storage. Question earlier, we are introducing thread local storage. We also have to address the dynamic initialization of static duration variables, i.e. global variables and function local statics. And we also have to address the destruction of those variables. The first thing we're going to do, probably the easiest thing, is adopt thread local storage. There's lots of existing practice for this already for pod structures, simple C types. And we do this the same way those compilers did. We introduce a new storage duration and a new storage class keyword. Each variable is unique to its thread, but each variable is accessible from all the other threads. So if you take the address of your thread local storage and you pass that address to some other thread, it can read and write to your variable. And a consequence of this is addresses of thread local storage are not constant. Those are created for each thread. We are also extending this to allow dynamic initialization and destructors for variables in thread local storage. And we've defined this very carefully to permit dynamic or lazy initialization of these variables. Because what you don't want to happen is when you start up a thread, it to have to instantly run around initializing thousands of thread local variables that it may never reference in the entire lifetime of the thread. So we're very much trying to be able to set it up so that you only have to initialize the variables at the intersection of the set of variables and the set of threads. So we want a sparse use of memory and initialization.
You initialize them when you take the address of one?
The question was, do you initialize it when you take the address of it? Well, what the standard says is that it will be initialized before first use of that variable. And so it gives the compiler a little freedom to push things a little further ahead. So what's permitted, for instance, is if you use a thread local variable in the middle of a loop, it might move that initialization out of the loop and do it at the top of the function. So there's a little leeway in where the compiler vendors can start that initialization. We can sort of do this all in the compiler, but OS support would provide us a little more efficiency. If I have a global variable that requires dynamic initialization, say it has a constructor, this gets tricky because what if I have two threads running and they both want to see this thing initialized, or they both try to initialize that? Without synchronization, we potentially have data races. With synchronization, we potentially have deadlock. And so we're going to break this apart into two problems. One is for function local static variables, and one is for the namespace type variables. And the reason is function locals already have this notion of lazy initialization, and we're going to capitalize on that. The first thing we're changing is that the current standard, of course, doesn't say anything about synchronizing these initializations. We have decided to standardize on making sure that those things are synchronized. So two threads who decide to initialize the same thread local variable, thread local static, will be synchronized. But while the initializer is running, they will not be holding a lock. Okay? You may still, other threads may be blocked waiting for that to happen, but there will be no new lock introduced and held for that duration. And this is made possible by a new algorithm developed by Mike Burrows here at Google. And Google has released this code into the wild under a friendly license. And basically what this algorithm buys us is we get on average a cost of one additional non-atomic memory load to make all of this work. It's really a quite subtle algorithm. For non-local static duration variables, that is, say, global variables, we've gotten a little bit tricky here. The current language doesn't let you, gives you sort of an indeterministic access to variables that are defined in another translation unit. So the only thing that's sure is what you access within your own translation unit. What we have done is change the current definition where it's either zero initialized or fully initialized to you don't know what you get. So what was sort of indeterminate is now undefined. So all you can really rely on while you're initializing the global variables in your translation unit is other variables in your translation unit. What that allows us to do is concurrently initialize the variables in two different translation units. Because as it turns out, concurrent initialization in some applications will help substantially.
How do you know that when writing code like this, how do you know that vector itself doesn't rely on some other variables from another translation unit?
So the question is whether or not vector relies on variables from some other translation unit. And the answer is the implementer of vector has to make sure that they don't do that. So Yeah, so it'll have to be part of the contract between you and your library vendor about what they do in terms of their implementation. Destruction has much the same property. So we also say that when you destruct, you can only rely on those same set of variables. The extra complexity here is what happens to function local variables that were initialized while initializing a global variable. And the answer to that is we interleave them properly and save it up for destruction.
Are the destructors run in the same threads as the constructors?
The question is, are the constructors run in the same threads as, are the destructors run in the same threads as the constructors? And the answer is, you don't know. Okay? And I'll get to that reason in a second when I get to termination. Yes?
I don't understand how you can do this concurrent reverse and expected not to deadlock. Because if anyone's taken the address of any variables that were statically initialized, then they could depend on that thing being held somewhere. I mean, it just can't work.
Right. So this model implies that you aren't going to be storing addresses in global objects that cross those module boundaries. So we had a lot of discussion over this. This is sort of the working compromise between basically forcing sequential initialization of all of the variables, which means that when your application starts up, you have this long period of being able to only exploit one thread, versus basically eliminating global variables because of the synchronization problems. So it's not an ideal compromise. I'd be really happy to sit down with people, and if there's a better idea or you think that this isn't going to work, please sit down with me. We'll go through it and try and make sure what happens, because we certainly don't want to release a standard that can't work. But we understand that what happened, this model here, will invalidate some current codes. We don't think it'll be too hard because what we've made undefined was previously indeterminate.
Indeterminate, but also a common cause of mysterious bugs.
And also a common cause of mysterious bugs. So now we're going to move into the sort of a library phase, and this should go quicker. The model that we have for threads is a fork and a join. And you fork a function to be executed, and then later you come through and join. And because of the magic of C++ operator paren, we can make the join look sort of like a function call. So this notion is very standard about what's being supported in the current operating system world. That view is common. We're going to stick to it. We are also going to support functor-like objects so that you aren't totally stuck trying to communicate through a narrow POSIX, only pass in your function pointer type of interface.
Why do you have extra parentheses in there?
Talk to me. So the question is, why are those extra parentheses there? Talk to me afterwards, and I'll explain to you a bizarreness in C++ syntax. Those extra parentheses have nothing to do with threads. The next thing is the scheduling of these threads. As it turns out, scheduling is a very touchy issue, and things are dicey. So we are probably in the standard going to only supply two mechanisms for scheduling threads. One is a yield, which says, now would be a good time to switch to somebody else. And the other is a sleep, which is, I want to go away for a while. Those are adequate for a lot of applications. They won't be adequate for all applications. For those other applications, we're going to give you a handle on the operating system thread. So you can ask us for your platform-specific handle to a thread, and then you can go off and communicate with your operating system detailed scheduling issues. We will also have a query to allow you to find out what the hardware concurrency is on your system. So this sort of gives you a measure of maybe what's the most number of threads you should fork off to be helpful. It's a very vague number because hardware is actually quite different. For synchronization, the base concept we have is a mutex, which is similar to what POSIX and Windows provide. We're going to have a notion of sort of exclusive, writer lock, and then we're going to have a reader-writer layer on that. And there are sort of four notions of locks in here, and mostly those are still the same exclusive, single thread lock versus reader-writer lock. The difference between these layers is sort of your right to change from being a reader to being a writer without having to give up the lock. So that's what these convertible, upgradable types of things are.
I understand what upgradable is. What is convertible?
So that is, you can convert from having only one person, only one reader can have convertible access. And when he wants to become the writer, he converts.
What's upgradable?
So I have to sit down and look at the APIs every time I try to answer this question, and I don't have those APIs there. So it's subtle in the transition states, and I can't remember exactly which one happens here, but it's all centered around being able to convert from read access, you hold a read lock, and being able to get to the write lock without releasing it.
From your slide, it looks like convertible is talking about between single reader, multi-reader, upgradable,
Yeah, that sounds similar. So the observation was convertible is single reader to multiple reader, and upgradable is I am the golden reader who can convert to writer. Now, so that's a mutex. On top of a mutex, we have a lock. And a lock is basically the state of owning a mutex, of controlling a mutex. So a lock is typically done as a function local object. It's a local variable in your function that provides both the acquire of the mutex and the release of the mutex. And these are coordinated with the mutexes. This is fairly common in some of the C++ libraries to make sure that you get mutex acquires and releases paired up properly. You're not required to use these things. We also have condition variables. Earlier versions of Windows did not provide condition variables. Later versions of Windows do. Everybody who's programmed on Windows and Unix pretty much agrees that the Windows events are much harder to use than the POSIX condition variables. And so we're standardizing on that approach. What condition variables allow you to do is upon grabbing a mutex, you've discovered the state isn't quite right for you, to release the mutex and have somebody notify you when the state is something that's appropriate to you. And once you have these, then you can write your code in the monitor pattern, which has a fair amount of literature behind it. And so here's an example of the conditions and where they get used. In particular, they represent extreme states. So for a buffer, we have conditions where the buffer is full or not full and not empty. So we represent the extremes, and then we can notify threads when we reach extreme states. The next thing,
Locks are non-reentrant, right?
the
Locks are non-reentrant?
The question is, are the locks non-reentrant? The answer is that's unclear right now. The committee hasn't fully decided whether or not to provide non-reentrant locks only, reentrant locks only, or 2 locks with the option. So we haven't quite settled on that yet. So the next topic we're going to talk about is thread termination. The first issue is voluntary termination. So if you run off the end of the function that was used to start the thread, you've terminated that thread. But there's a lot of applications where the natural thing to do with a thread is to put it in a loop waiting on some external event. And you want to shut it down some way. So the application, in fact, doesn't terminate of its own accord. It wants to be told to terminate. And for that, we need some way to signal to the entire application and all of its threads that it's time to quit. And the committee has strong opposition to asynchronous termination, because asynchronous stuff going on in C++ is just nearly impossible to code properly. So the committee has strongly voted against any form of asynchronous termination. So now we're left back to synchronous termination. And the only way to really make this happen is if in one thread I signal to another thread that it's time to terminate, and that second thread perceives that as an exception. So let's take a little digression here and ask, well, what happens if a thread has an exception that it doesn't handle? The exception runs off the top. Well, do you call std terminate as you would if an exception popped out of main? Do you propagate the exception to some thread trying to do a join? Do you just ignore the exception? And the answer to that is we haven't fully decided yet. There's various issues either way you do it. Any way you do it, you're going to make somebody unhappy. But we have sort of decided that what we need very definitely is a way to manually propagate. So if we assume in the simplest case we just call terminate, then we're going to need a way to manually propagate an exception from one thread to the other. And that, in fact, requires new language facilities, because right now we have no way to sort of store and forward an exception. So what happens back to cancellation? We've already sort of mentioned that cancellation will be perceived as an exception in the second thread that's being told to cancel. The question is, will that thread be ready for it? When will it see that exception? In the case where you're not ready for it, we have an API to say, I'm not ready for any cancellations now. And so any cancellations will just sort of be noted and will not actually appear as an exception. And then when you become ready to deal with a cancellation, you can then pick up that exception. Within that range of things where you're not quite ready for one, you can explicitly test for whether or not a cancellation is pending. And you can simply ignore things. But in the normal case, you will get an exception. But you won't get an exception at arbitrary points in the program. You will get an exception only at cancellation points, places where we know it's safe to cancel you. And those are, based on this list here, just the synchronization points where you're likely to be blocking or doing some other act like that. So What comes out of all of these things is potentially, instead of what you were expecting, an exception saying you've been canceled. There is, however, a problem in all of this. None of those points included I/O operations. So if you are blocking on I/O, a thread is blocking on I/O, you now have no way to cancel it. And if the I/O it's waiting on doesn't show up, it's going to be hanging there forever. So we know this is a problem. Partly it's a weakness in the current operating systems, because many of the current operating systems don't guarantee that you will wake up from an I/O operation if you cancel a thread. So the C++ committee is trying to work out, in conjunction with some other committees like POSIX, what we can do to make sure that we have some way to cancel threads that are blocked on I/O. And we don't have a resolution on this yet. And then going beyond what we're putting into the standard, we want to try and enable libraries to handle the heavy lifting. So most of what I've shown you here today is primarily the lowest layer that most programmers will never see, that they will work through libraries at a higher layer. And the question is, how do you get to that higher layer? The first task is probably things like thread pools and thread groups that the C++ standards committee will define in terms of a technical report. There's still an open debate about how much of that will go into the next standard and how much will be deferred to the actual technical report. But the issues for deferring these things add up, among them being we aren't quite ready, we don't know how much we want to force early, we still need specification work, et cetera. And the standard is looming very quickly. What would we count as success? Well, one of the things is, can we build libraries? And the answer to that is, we believe that as of today, that we can build all of the facilities that we're trying to implement in the second technical report using the facilities that have been proposed for the next C++ standard. So we have sort of evidence that at least the first round of libraries can be implemented with what's being defined in the standard. And we believe then that you can pick up and define your own set of higher level libraries beyond that. One of those examples is futures that we're contemplating putting in a technical report. And basically what a future says is, go off and compute this function, and later I will come back and ask for the return value. The fork join model that the standard is proposing doesn't provide for return values. It's all void. So what happens if you want those return values? Futures is a means to happen that. What happens if the thread exits with an exception? You want to be able to get that exception at the time you ask for the return value. And the advantage here is that now you have a simple mechanism to take sequential code and, using the futures, turn it into parallel code. And for those interested in reading the actual papers, those are the paper numbers. But we have a big hole right now in the standard. And that is, the proposed standard does not have a mechanism for lambda. For the purposes of parallel and concurrent programming, what we really need is basically an anonymous nested function, something like out of Pascal. There's a group. We're late, but we're trying to get this done in time for the standard. So if we can put that in, then those lambdas provide you an extra layer of functionality and capacity that really helps you write good libraries, so that you can write a parallel for loop entirely in library code. So the conclusions are, the basics are on track. Most of the core language stuff, we could probably go with what we have today. We are still fine-tuning it, maybe trying to loosen the model in certain places so that we can support more loosely coupled hardware. And the basic model for launching and dispatching threads and synchronizing, all of that is there. We're still working on detailed syntax and detailed semantics, but we're basically on track there. Some of the features need work, like this destruction we talked about, to make sure that we're right there, making sure the exception propagation is solid, and getting these cancellation, lambda, the higher level issues in. That's where we've got the biggest work ahead of us. And then, of course, the real value to all of this is not when we are done with the standard, but when you pick up the standard and write the libraries, write the facilities, build on top of what's in the standard, and you know, put it all in open source and so forth. Question?
You've never talked about dynamically allocated atomic variables and locks. At what point do these things come into existence, and how do you resolve races between creation and destruction of atomic variables and their operations?
Okay, so the question is, when do these dynamic allocation of atomic variables and locks, and when do those get handled? First, the atomic variables have what are called trivial constructors. So they come into existence basically either completely undefined because you failed to provide an initial value, or they have a defined initial value. So there's no possible race on creating them. Once you have their name and can reference them, they're already initialized.
You can have races on creating them. Let's say I use an arena allocator. I just deallocated a piece of an object which has non-atomic variables, which have loads and stores.
Okay, so
then I create a new object with an atomic variable on there. The previous operations were non-atomic, and they can race with
and so the question is, what happens if you have an arena allocator, and you're basically reusing the same memory, right? The atomic variable, the operations, the atomicity comes not with the initialization, but with the first atomic operation on it. So anything you do before that first atomic operation is prior history, sequential history. So that first atomic operation, the reason that first atomic operation is good is that the initialization is well defined. And the initialization is done before the atomic variable comes into existence. So the normal semantics is that variables that are dynamically initialized are zero initialized before that variable's name is released. And because they're zero initialized, we have a good state at the start of the atomic variable. Okay? Now, for mutexes, the story is different, because most of the mutexes from the operating system require that you do some initialization operation on the mutex. And for that, it has to be done by one thread, and you have to make sure that you don't let the name of that mutex out until after it's initialized. So you don't want to pass the address on until after you've initialized it. Now, for destruction, the atomic variables also have trivial destructors. So basically, they are never destructed. They're always valid. They'll be valid until the end of the address space. The mutexes from the operating system, they also often have that same trouble if you have to call a specific function that says, OK, this mutex is now over with. And you have the same problem there that you had with the initialization. Make sure that you've taken away the address to that mutex from all the other threads before you bring it down.
Can you legally create objects, like reference counted objects which have mutexes which delete themselves when the reference count goes to 0?
The question is, can you have reference counted objects that delete themselves? The answer is yes, you can. But you have to be careful to make sure that the reference count is such that you don't let anybody else in. So you have to set things up in the right order. And reference counted objects in an atomic world are not trivial. So
The mutex is the problem.
yeah, the mutex can be handled because you can undo the mutex while still preventing access with an atomic variable. So you can use an atomic variable to stop people from trying to do a double operation on the mutex. Question?
Is there an effort to implement, like we do in other new C++ features on, say, GCC?
Okay, so
you would have, there is some support in GCC already for some of these things.
yeah, the question, I'm going to expand your question a little bit. And the question is there prototyping information of efforts underway for any of this kind of stuff? The answer is that for the standard in general, there's a fair amount of prototyping effort going on within GCC to prove certain higher level features are in fact implementable for the next standard. There hasn't been any prototype work for a lot of the lower level stuff here directly for this standard. The atomic stuff has been justified in part because a lot of the prior work out there is very, very similar to what we're standardizing. So for instance, the atomic operations, there's two lines of reasoning that say it's implementable. One is the paper that proposes it has the bare minimum implementation in it. And then it points at the GCC and Intel _sync primitives that say the rest of it has already been implemented by GCC and Intel compilers for this alternate syntax. Now, the one place where we have a real weakness here is in the implementation of the concurrent variable initialization and destruction. There is no implementation of that yet.
Maybe we could get that going on that branch?
Yes, the question is maybe we can get that going. And yeah, I would like to get that going. And every time I sit down to start on it, I get interrupted. And so if somebody out there has some spare cycles and wants to help work on this, happy to hear from you.
What does N2169 mean?
Oh, OK. So the question is, what does N2169 mean? So the C++ standard works in terms of working papers. So people write a paper describing a need and a proposal and so forth. And then that gets a document number. And we start at N1, and we're now at N2169. And so that's the paper that is on some certain topic. This N2169 is a paper that's describing all of the features that are being tracked for the next C++ standard. So all of the proposals for the next standard, it's tracking all of them and giving you sort of an overview of where everything is right now. And a subset of that is all the threads, all of the papers dealing with multi-threading. And unfortunately, there's no overview paper for threads. You get an overview for the entire standard or individual thread topics, but not for the whole, for the thread domain. Any more questions? Well, thank you all for coming.